Okay, so here now we are going to learn about compound microscope. In the last session we had seen a simple microscope. You might be wondering that we have done so much problems on lenses, and we had used a single lens with a two which are separated by a distance d, lenses which are in contact with each other. After doing all these lenses, what is the point in again relearning those lenses in this particular form? So what is the point in learning a simple lens, or why it is called as a simple microscope? Here the theory and the equation which are going to be used for a microscope is nothing different from what we have learned for the lenses. लेन्सेसचे इक्वेशन जे आहेत तेच आपण मायक्रोस्कोप आणि टेलिस्कोप करता वापरणार आहोत, पण त्या लेन्सेसचा आपण उपयोग एका इन्स्ट्रुमेंट हुज नेम इज मायक्रोस्कोप त्याच्याकरता आपण करतोय, जे ह्युमन आईसाठी आपण तो इन्स्ट्रुमेंट वापरतोय टू मॅग्निफाय सर्टन ऑब्जेक्ट्स. म्हणजे लेन्सेसचा उपयोग पण तोच आहे, पण हा स्पेसिफिक ॲप्लिकेशन ऑफ लेन्स फॉर मायक्रोस्कोप. आणि मायक्रोस्कोप स्टडी करण्यासाठी आधी बाय डिफॉल्ट यू हॅव टू स्टडी अ सिम्पल मायक्रोस्कोप अँड देन यू हॅव टू स्टडी अ कंपाऊंड मायक्रोस्कोप. So as a basic formality, a simple microscope means using a simple convex lens, and a compound microscope means using two convex lenses. Okay, so whenever they mention microscope, which means simple or compound, आणि जर ते simple असेल तर it is a convex lens. It cannot be any other lens like plano convex, concave lens, concave convex. ते जे वेगवेगळ्या कॉम्बिनेशन्स असतात लेन्सेसच्या त्याच्यात इन्क्लूड होत नाही. दिस इज सो इन शॉर्ट वेन वी टॉक अबाउट सिम्पल मायक्रोस्कोप इट मीन्स इट इज ओनली अ डबल कॉन्वेक्स लेन्स. करेक्ट. सो इट बिकम्स व्हेरी क्लियर what type of lens it is when they mention the word microscope in the problem. And when they mention the word compound microscope, it means they are going to use two lenses and both of them are going to be convex lens. Now all these equations what we are going to do with the microscope are, as I have said, nothing different from what we have done from normal lenses. The same equation of magnification, the same lens maker's formula, the same equation of 1 upon f is equal to 1 upon v minus 1 upon u. All those things we are going to use, but we are introducing a new terminology while we are learning simple microscope or compound microscope, and that is about DDV. That is the distance at distinct vision. Using this DDV, we are going to derive the equations. Are you getting the basic difference what we have done in the last sessions of lenses, right? And this session about microscope is that first thing, it is only about convex lens when we talk about microscope. Second, we are introducing a term which is known as DDV, that is distance at distinct vision. मग ह्या DDV पासून आपण मागच्या वेळेस इक्वेशन घेतलं होतं फॉर सिम्पल मायक्रोस्कोप. रिमेंबर व्हॉट वॉज द इक्वेशन? दॅट द मॅग्निफाइंग पॉवर वॉज गिवन ॲज D upon FE. D upon F. F was the focal length of that lens. So the last equation which we had done was the magnifying power was 1 plus D upon F. Okay, so what was D? D is the distance of distinct vision. D is your distance of distinct vision, and this was the magnifying power when, like as you can see over here, it was this kind of a lens, simple microscope, an object was placed over here and a virtual image was formed over here. So in that, if you remember, we had two situations. One when the image is at DDV, and another when the image is at infinity. So this was the situation where the image was at DDV, and if the magnifying power was given as D upon F when the image was formed at infinity. This is, you have to remember these relations, because these relations are a bit different from our normal magnification which we are using for convex lens. You know, for minus normal magnification, what are the equations that we were using up till now? That is distance of the image upon distance of object or height of image upon height of object. You recall we had solved problems based on these two equations. Now this is about the magnifying power in a different terminology. In the form of DDV, this equation has been established. So similarly, we are also going to establish a similar equation for a compound microscope. Now come back to this diagram. As you can see here, though you might feel a bit complex diagram, but it is a simple ray diagram. The lens, which is, this is a microscope. As you know, you have used microscope in your experiments with your 10th standard. In the microscope, there was a knob which used to move. So while moving the knob, what were you doing? You were actually changing the distance between these two lenses. You were changing the distance between the two lenses till you used to get a sharp image of the specimen. Got it? So there was one lens which from where you used to see, that was called as the eyepiece, and there was one lens which was near to the specimen, you know, that slide which used to put in the microscope to observe the specimen. So there was a lens which was nearer to that specimen. That lens is known as an objective. Size wise, as you can see here, maybe I have shown in such a way, but it can be a bit confusing, because you might think this bigger one to be an objective and the smaller one to be an an eyepiece, because you knew that the eyepiece was very small. But these are relative diagrams. The manufacturing of that diameter of that lens can be made of any diameter, correct? So that eyepiece, which is actually a thin lens, and this is a fat lens. As you can see, what I wanted to emphasize over here, that this is a thin lens and this is a fat lens. The basic magnification will be done over here, and this will be the second magnification done on the specimen or on the object. For the biology students, it will be called as a specimen, but for physics, that specimen will be considered as an object. Okay, so we get a very highly magnified image when we are making use of two lenses in this particular arrangement. All the other equations, all the other parameters are going to be the same for all the other equations that we have been doing up till now. So don't get confused that why for a compound microscope is there some new relation. There is no new relation. It is the old relations of the lenses, but we are trying to represent it in the terms of the definitions of a microscope, the construction of a microscope, the parameters of a microscope, in which DDV plays a very important role. Got it? So here you have seen this. These are the two arrangements. This is called as an objective, which is placed near to the specimen, and this is the eyepiece through which you observe the magnification. Now our specimen is nothing but object AB. You can see over here, this object AB is nothing but the specimen which is kept in front of this objective lens. Okay. Now this objective lens will form an image that is A2, B2. Can you see this image? A2 and B2, which is formed by a normal, I'm very sorry, A1 and B1 is the image which is formed by this objective lens. So AB is forming an inverted image A1, B1 on the opposite side. Ignore this lens and ignore this image now. So this is a normal ray diagram. It's converging and I'm getting an inverted image. Can you see the inverted image? Inverted image means what? It is a real image. Inverted image, it's a real image in a convex lens, and that is what exactly we are getting over here, which is a real image. Now what we are doing is, we are not satisfied with the magnification of A1 and B1. A1, B1 is magnified image of AB. That is definitely there, because AB is near to the focus. Remember our configuration, when the object is coming near to the focus, the image will tend to go towards infinity. But here we have not brought it at the focus, so we have brought it just before the focus, so the output is magnified. And as you know, as the object starts coming towards the focus, the image starts getting larger and larger. Okay, so we are getting the optimum magnification by placing this as near to the focal point, but not on the focal point. So what do we get? We get an image A1 and B1, which is real and which can be formed on the screen. It is inverted and enlarged. Now what are we going to do is that because we have got a real image, we are going to take the advantage of its realness and we are going to place another lens. See, we are placing another lens in front of it, but we are placing the lens in such a way such that the image is between the focal length and the lens of the convex lens. You can see FE is the focal length of this lens. Now the image is placed between focal length and the lens. As per our diagrams that we had studied for lenses, when an object is placed between a focal length and the pole of a lens, what kind of an image is formed? The image formed is virtual, correct? It is erect and highly magnified. That is exactly what is happening. I am having an image. Since it is a real image, it can act like an object for this lens. That real image is acting like an object for the second lens. I had told you this is a chain method of finding the final image when there are more than 2-3 lenses in contact. We had done problems on silvering of mirror, we have done problems on lenses, combination of lenses, and what we had seen is that the image produced by one lens will act as an object for the other lens, right? And it will produce an image, and that will be the final image of the basic object. So here, this was the basic object. It has formed a first real image, that is A1, B1. The another lens is kept in such a way so that this particular image should fall between FE and the pole. That is where the adjustment is done on the knob. The adjustment which you were doing, it was basically this thing that you were doing, that is placing it between the focal point and the pole. Now by doing this, what do we get? We get a more highly magnified image. First, as it is with this particular situation, we had a magnified image, but by placing it within the focal length and the pole, we are getting a virtual image, that is A2 and B2. Can you see this virtual image? This virtual image which is formed is A2, B2. Now this virtual image is a very highly magnified image as what is expected from a microscope. So you are able to see the cellular structures, you are able to see those bacteria, you are able to see the blood cells, right? Because it is magnified by two such lenses in combination. Okay, so this is the basic criteria. Now here probably you might be thinking that this image is virtual, is formed on the same side. This object is on the left hand side of this lens. Image is also formed on the left hand side of that lens. So what is this basically? Now up till now we used to show an erect object in front of the lens between the focal point and the pole, and the image was also was erect. Erect means what? Being erect means in the same direction of the object is called as erect. So here the direction of the object is inverted and the image is also inverted. Therefore we say the image is erect. This erectness is a relative term with the reference to your object that is placed on the principal axis. Is that clear? Okay. So this is what the image is. It is virtual because it is formed on the same side. It is highly magnified. You can see it is highly magnified and it is erect. Okay. So don't get confused by the word erect while I am showing this image as inverted. But here both the object and image are inverted. Therefore, it is considered to be erect. Okay. So after you have understood this, now let us see the basic equations that will be formed from this particular part. This was as far as the explanation part was concerned. As I have been repeating that the easier part is the explanation part in physics of how things are formed, how objects are seen, how the phenomena works for different machines and for different relations of various scientific what you call objects, or like we are talking about lenses. But the real part is, or the difficult part is to understand these equations, and the more difficult part is to use this equation to solve the problems. So after you have understood the basic arrangement of a microscope, let us go to the next part, and that is getting the relation and the equation for a microscope. Now things are very simple. We have to first have the relation of the basic object, that when an object is viewed by an eye, what is the alpha? That is the angle subtended by an eye to see a naked object without any instrument. So we always write that tan alpha, so tan alpha is going to be equal to AB upon D. So this is going to be your tan alpha. Now here, as you will see, this is the deviated ray which is passing through A1, B1. This is a normal ray optics diagram that we have been drawing up till now. So here I have given this angle as beta. Can you see this is your angle as beta? That means B1, P and A1 is angle beta. So if I find the tan of beta, so how will it be written as? Tan of beta equal to A1, B1. I can also use A2, B2, but I am using A1, B1. That is A1, B1 upon this distance, that is distance P and B1. But P and B1 is nothing but UE. What is UE? The distance of the image A1, B1 from the pole. We give U as the distance of object, no? But why this subscript E? Because it is an object for the eyepiece. All these terminologies try to understand. V0 is the first image created by the objective lens, so it is called as V0. U0 is the distance of the object to the lens, so it is called as U0. VE is the image distance from the lens of an eyepiece, so it is called as VE. Right? Please make a note of this important subscripts that we have used for U and E, because we have got two lenses. In the simple microscope we had only one U and E. So here we are going to use two E and E's. Now as you can see over here, this is your A1 B1 upon tan beta, A1 B1 upon UE. So this is going to be the tan beta, and we had seen the approximation theory in which approximately tan alpha will be almost be equal to alpha, and this will be approximately equal to beta. Because of the small values of that angle, tan alpha can be considered to be equal to alpha, and tan beta can be considered equal to beta. Now as you can see that we have the magnifying lens, that is alpha is the angle subtended on a basic object, whereas beta is the angle subtended on the final image A2, B2. So in what can be considered, how can we discuss, or how can we describe the magnifying power of a lens? The magnifying power of a lens can be described as beta upon alpha. So beta is larger than alpha. The higher the angle of beta, higher will be the magnification, because alpha will be fixed for an object, no? At a distance of ddv, the angle subtended by my eye will be fixed alpha, and depending upon how huge the object is, my angle of alpha will keep on increasing, no? Because if the object keeps on increasing more and more, right, my angle will keep on increasing. So therefore this angle beta basically decides the magnifying power. So you have magnifying power which is beta upon alpha. Let us put the values of beta upon alpha. So that can be written as beta is A1 B1 upon UE, that is your beta that we have taken A1 B1 upon UE, upon alpha, that is equal to AB upon D. So magnifying power can be written as A1 B1 upon AB into d upon ue. So this is our magnifying power that I am going to get as a1 b1 upon ab into d upon ue. Now what is a1 b1 upon ab? Now a1 b1 upon ab from this lens is the height of object is equal to height of image upon height of object into d upon ue. Okay, we know in our equation that we have done up till now that height of object upon height of image is also considered to be as distance of image upon distance of object. So this can also be written as now this is for which lens? It is for your objective lens. So it will be distance of image, that is distance of VO upon UO into D upon UE. So V0 is the distance of image upon distance of object. You have understood what I have done? We had this basic equation of magnification, no? M was equal to height of image upon height of object upon V upon U. This was the equation that we were using for solving the problems of lenses. So using the same equation, but instead just for V and U, because it is an objective lens, so I have used V0 upon U0 into D upon UE. Okay. From this again we will have two cases. Case number 1. So in case number 1, if it is at infinity, look here, D upon UE is what? The magnifying power of simple microscope. Go back to your last session and see D upon U0. We had just derived this, that D upon UE was the magnifying power of a simple microscope. So the total magnifying power, and V0 upon U0 is what? The magnification of a convex lens. That is your objective. So this magnifying power is nothing but is the magnifying power of objective into magnifying power of your eyepiece. This is your basic relation, that the total magnifying power is the product of the magnification by the eyepiece and the magnification by your objective lens. While I am teaching you, try to understand that these are the relations that are going to be useful for your CET examination and the problems based on that. Don't just take this as a derivation, as a theory. These are the relations which you are going to use to solve problems. You might feel that magnifying lens and the microscopes are very simple, equations are very simple, they are no doubt they are simple. But when they give you certain data, okay, so it can be very confusing that how the data has to be used for which of the relations that has been taught to you. So this relation, as I have given you, that is magnifying power of objective into magnifying power of eyepiece, if they give you directly two particular values and they ask you the final magnifying power of a microscope, so you should know it is a product of those two magnifying power and not the addition of the two magnifying power. That is what I am trying to emphasize at this particular point. It could be a simple problem. Every time all the problems are not complex problems, but the simpler problems are from those particular area which can very easily confuse a student, and you will start wondering, and then again you will not be sure whether this is the right answer or this is the right approach or not. Okay. So when it comes to magnifying lens, whenever they use the word simple microscope or a compound microscope, this equation should be there in front of you. Right? All these equations should be there in front of you, because from that point of view you are going to solve the problem. You will not be solving problems of microscope or telescope using our conventional lenses equations and problems, because it will become a very huge problem. Okay. So and it will go beyond your time limits. So you will have to learn these equations on these particular topics. So as I am teaching you, or as you are learning these new things, please keep entering all these equations in your formula books. Okay. So because after some time, some months, you might tend to forget about these derivations, because in the derivations in your JEE Mains, NEET and CET, derivations are not going to be asked, right? So it will be your equations that you have to directly use to solve the problem. So that is a basic task for you, to keep recalling equations from the topic wise. So whenever lenses or microscope is mentioned, so you should, all these equations should be there in front of you. So in that, now we will see 3 more equations which are going to be defined based on this final equation. Now here, as you can see, it is V0 in case 1, it is V0 upon U0 will remain the same. So magnifying power will remain the same, that is V0 upon U0 into D upon UE in the simple microscope was replaced by D upon F and 1 plus D upon F if the image was at DDV and if the image was at infinity. The same 2 cases equation will be applied for this. So now this U will be replaced by this equation, that is going to be 1 plus D upon F, but now this will be F of eyepiece. Look here, for a simple microscope it was just one F, it was not mentioned it was FE or FO because it was comprising of only one lens. But here, since we are using 2 lenses, we have to specify the focal length of which lens. Don't make mistake, here it is the focal length of the eyepiece, correct? Now the derivation from D to D upon UE to 1 plus D upon FE is given in your last session for simple microscope. Please refer to that, how D upon UE gets converted into 1 plus D upon FE, right? I am not going to explain the same thing again here. Now similarly, in the case 2, or let us discuss the case 1 further. Now in this case 1, this was when the image was at DDV, distance of distinct vision. When the image is at DDV, this will be the magnifying power that you have to use in your problem. Now there is one more terminology which you have to understand while doing the while understanding lenses, or while understanding microscope, and that is called as the length of a microscope. So whenever a data is given to you as the length of a microscope, is the distance, the length of a microscope is given as LD, right, and which is the distance between the 2 lenses. The length of a microscope is nothing but the distance between the 2 lenses. These terminologies are very important, that is why I have written it in words, that length of the microscope, because in the problems they will be giving you the problems in these words. It will not be a specific problems of giving you the data, which means when they say the length of the microscope is 10 centimeter, so they are telling you the distance between the 2 lenses is 10 centimeter. And what is the distance between the 2 lenses in terms of, as you can see, it is V0 plus UE. So it is written as V0 plus UE is the length of a microscope. Okay. Now we are going to work within some certain approximations. Now this is a very specific equation. If specific data is given, you can find the magnifying power of a microscope. Just try to understand how the problems would be given, that for a compound microscope, the moment they use the word compound, which means there are 2 lenses. The image was formed at infinity, so you know you have to use this particular relation. And they will say the length of the microscope was so much. And when the length of the microscope is given, and I want to find the object, that is eyepiece object, was kept at a distance of 2 centimeter, right? In any of this equation, UE is not required. UE is not required. That is the distance of distance created distance of the image from your lens. Okay, so LD is V0 upon UE. Now if this distance, if they give you, specify and they specifically tell you UE is so much, so from that you can find V0 if the length of the microscope is given, and this V0 you can replace over here to find the magnifying power. So all these words, the sentences, as I say, the length of the microscope, magnifying power of a microscope, all these words are very important. DDV, right, when you are going to solve problems of this type. Now length of a microscope, we are going to do certain approximations. So in these approximations, what are we going to do? Let us see. V0 will be approximately equal to how much? What is V0? V0 is the distance of the image from the object. Okay, so V0, as you can see, this image is for drawing the diagram. I had shown this Fe at this particular part. The Fe of this could be more shorter, right, because the magnification required is much higher. If this Fe is shorter, then what will happen? This image will almost be formed somewhere over here. Once again I am repeating, if the Fe is shorter the Fe, higher is the magnifying power. Just understand, longer the F focal length, lesser is the magnifying power. So when the focal length is reduced, right, and if the object is placed between the focal length and the pole of the lens, so this image will be almost as close to the, very close to the lens. Do you agree? This image will be very close to the lens. In that case, the V0 is almost equal to LD. Only a very small distance will be left for UE. UE will be very small. It will be so small that it will be neglected. So I can say V0 will be almost be equal to LD. Will be almost be equal to LD. Okay. And what will happen to, let us give the approximation for U0 also. Normally U0 is kept very close to the lens. You must have seen that lens is almost touching the specimen when you are inserting that slide. So if U0 is very near to that, again it will be almost on the focal length, as I said, but not on the focal length. So I can also use the approximation that U0 is also approximately equal to the focal length. It is almost on the focal length. This object is almost on the focal length, but not on the focal length. But we can approximately use U0 equal to the focal length. In this particular case, then what will be my magnifying power? My magnifying power is going to be V0, that is LD upon F0 1 plus D upon Fe. Right? These equations are very, very important from your CET and mains point of view, because this equation what I am giving you is not available in your textbooks. This is all the extended equations which I am giving you from solving the problems for your CET and JEE mains. This was the normal derivation which is there in your textbook, which is used for your board exams. Okay, but this equation what I am giving you right now are specific to problem solving for your mains and CET. So please make a note of this. This is an equation which you have to again enter into your formula book. See here, what are the terms? LD, that is the length of a microscope, is given to you, and they will give you the focal length of both the lenses, and they will ask you what is the magnifying power. DDV, no, DDV, the distance of distinct vision, is normally approximately taken to be equal to 25 centimeter. Okay, so by using these three relations, you should be able to find the magnifying power of that. Now, when we look at case 2, so in case 2, what do we have? We have the magnifying power. The magnifying power will be equal to, again, when the image is at infinity. What is case 2? When the image is at infinity. When the image is at infinity, we have a case 2. So MP will be equal to D upon F. So in this case, the total means 1 plus D upon Fe will be replaced by sorry, excuse me, D upon Fe, just D upon Fe, not 1 plus D upon Fe. Now here again we are going to use the same approximation, but when image is at infinity, LD will be this LD that we have discussed. LD will be equal to image, that is V0 plus UE. Okay, V0 is what? Distance of the object, and it is going to be V0 plus Fe. This will be the V0 is the distance of the image, and this is what we call UE, no? So U is the image will be exactly taken on the focal length. The lens will be so adjusted that A1 B1 will be on the focal length. That is the reason, no? When the object is on the focal length, the image will be at infinity. So when image is at infinity, UE will be at focal length. So LD will be V0 upon Fe. So we can write your MP is equal to V0, and as I've said that V0 is almost equal to LD. So it will be V0 plus Fe, and U0 will be equal to F0 into D upon Fe will be the magnifying power which has to be used for your what you call compound microscope in the case in the situation where image is at infinity. Here when the image is at DDV, and the length LD of the microscope in this case is V0 plus UE, and this is V0 plus Fe. Normally UE is the distance which cannot be obtained because it is a virtual distance. That image distance cannot be measured. No, how can I measure the distance between the image and this? Right? So finding UE is very difficult. Distance of object through some scale I can measure. Right? Even the image I should be able to measure, but UE I cannot get. Right? So that is why it is more easier to find the LD, that is the length of a microscope, with this when the image is placed at infinity. Okay. So please make a note of this, and these are the two important equations of MP. One MP, this is your generalized equation. This is your generalized equation of MP, right? This is a specific case. This is again a generalized equation in terms of image at infinity or image at DDV. Now this is the derived equation. So the problems can be asked in any of these four options. You should be knowing all these four relations for a compound microscope, and for a simple microscope these are the two relations that which you have to understand, right? So please make a note of this.